So we'll start off. So based on talking to some people working on some exercises from the notes, I just wanted to bring up a few points in terms of things to know. I think it's a good thing to just commit to memory when is -1 is square mod p. Here p, if I forget to say, is an odd prime. You should just know when -1 is a square mod p, so you don't have to look it up all the time. You should know when 2 is a square mod p. You could think of it as 1 or 7 mod 8, or plus or minus 1 mod 8. Maybe that's easier. To be honest, I've never been able to remember when -2 is a square mod 8, except I set an exercise for it, so I know it's when p is 1 or 3 mod 8 now, but 2 months from now, who knows? And if you have to calculate the non-zero squares, at least for 3 and 5, you should just know 1 is the only non-zero square mod 3, 1 and 4 are the only non-zero squares mod 5. For 7, I never really remembered that it was 1, 2, and 4, except I've taught some number theory courses enough times I learned that. I don't know what the squares are mod 11. But it is good to know there are p minus 1 over 2 of them. So if you find some and you get that many, you just know that you're done. And also, although it seems like a minor point, it is convenient just to know that when a is any odd number, a squared is 1 mod 8, not just 1 mod 4. A squared is always 1 mod 8. You could just go through 1, 3, 5, and 7, or maybe more simply, write them as plus or minus 1 and plus or minus 3. Then it's easier to see. Oh, you square them. You just get 1 and 9. They're both 1 mod 8. Yeah. OK, so with that out of the way, I want to go back to what we were discussing last time at the end, and that was discussing when you can write a prime in the form x squared minus dy squared, which is an integer, not a square. We're, of course, not interested in writing numbers as x squared minus 4y squared. I mean, that factors, so not so interesting. And so if d is not a square, when is p is x squared minus dy squared? So a necessary condition is that we saw yesterday, if you're going to be able to do that, is d has to be a square mod p. And it's natural to ask, what about the converse? Because checking that a number is a square mod something else seems like a small calculation versus solving in integers, finding x and y to make p equal to x squared minus dy squared might seem like a more substantial thing. An equation in the integers versus a congruence. But quite often, the converse is, in fact, true. And as 2 examples, when d is -1 or when d is 2, the converse is true. If -1 is a square mod p, p really does have to be, well, x squared plus y squared. We're taking here d equals -1. So x squared minus dy squared is just the sum of 2 squares. And when d is 2, when 2 is a square mod p, p really does have to be x squared minus 2y squared. So that's when d equals 2. But the converse direction, and maybe since I'm talking about converse, I shouldn't write double arrows, but just write the single arrow. Under the modular arithmetic condition, we can solve an equation in integers. So this direction, going from a congruence to solving an equation in the integers, is not always true. And we saw at the end of last time 2 counterexamples when d is 10 and p is 3. So d10 is a square mod 3, but 3 is not x squared minus 10y squared because it doesn't even work mod 5, because we know the squares mod 5 are 1 and 4. It doesn't include 3. And 3 is a square mod 11, but 11 is not x squared minus 3y squared because, well, reduce mod 3. 11 is 2, which we know is not a square mod 3. So the converses can be false, but there is a nice condition on D that tells us the conditions under which the converse is true. And it's really not a condition so much on the number D, but on the ring Z bracket, the square root of D. So we have a very nice theorem. When you have an integer that's not a square, and the ring Z bracket root D by which I mean all the numbers of the form a plus b root d. So when d is -1, this is the Gaussian integers. When this has unique factorization, so this brings in a ring theoretic condition, or as people abbreviate it, it's a UFD, unique factorization domain. When d is not a square and the ring z bracket root d has unique factorization, for primes p, we can go in that converse direction. D being a square mod p, actually, well, we can almost do it. Plus or minus p can be written in this way. So we may not be able to get p, but we can get plus or minus p. And actually, the direction we discussed yesterday with p being x squared minus dy squared implying d is a square mod p, the reasoning goes through if you have a minus p in place of a p, because when you reduce mod p, the left side is still equal to 0. So we could say, in this case, that both directions work. When d is a square, that's equivalent, or maybe, that's equivalent to writing plus or minus p in this form. So I guess just to clarify, when I write plus or minus p, I mean either it works for p or it works for minus p, or both, but you may have it hold only for maybe minus p and not for p itself. So for example, well, so for which d have you seen, do you know that z bracket root d has unique factorization? Yeah. For z bracket, your first go-to answer is 3. Okay? Is that the first one you ever saw? Z bracket root 3 has unique factorization? Z bracket I, z bracket root 3. Maybe we should start here as a comma. No. That's 1 plus root minus 163 over 2. Oh, yeah. Yeah. Okay, so z bracket root d. I'm not going to write them all down because we expect it to happen infinitely often, but just as examples. So d equals -1, that's the Gaussian integer. This is probably the first example people see. What other examples have people seen? You said 3. Anybody seen 2? Z bracket root 2? Z bracket root -2? Plus or minus 2? Can I say plus or minus 3? No. Not -3. Z bracket root -3 does not have unique factorization. It's somehow too small. And how have you seen this shown? Forget algebraic number theory. How have you seen it shown that these have unique factorization? Yeah, you usually show it's a Euclidean domain. In fact, typically in undergraduate algebra, the only method you ever learn for showing something has unique factorization is to show it's a Euclidean domain. There are other methods. Even if such a ring does have unique factorization, it may be really hard to actually show it that it's Euclidean. So a famous example, famous to me, is z bracket root 14. In fact, has unique factorization. This factor is sort of, in principle, known, maybe in another language. I don't mean like German. Well, I guess Gauss did it, so maybe. But in like the language of quadratic forms, in some sense, it was known that z bracket root 14 had unique factorization, like since the early 1800s. But the first proof that it's Euclidean only came about like around the year 2000. So yeah. Anyway, but at a basic level, the first method you learn is to show the ring is Euclidean, but I'll just say, if you've never seen other techniques, there really are other methods to decide if z bracket root d has unique factorization than trying to show it's Euclidean. Okay, anyway, maybe I should also say not for d equals 3 or plus or minus 5. Neither of those work. Okay, so yeah, so we have this equivalence, and as an example to appreciate the case z bracket root 3 is a UFD, and taking d equal to 3 is a square mod 11. This is what I was mentioning on the previous, earlier. 3 is a square mod 11. So here we're taking d equals 3 and p equals 11. And 11 is not x squared minus 3y squared, because you reduce mod 3. 11 is not a square mod 3, but the theorem is saying that 3 is a square mod 11, plus or minus 11 should be of that form. You see minus 11, does anybody see how to write minus 11 as x squared minus 3y squared? Yeah, 1 squared minus 3 times 2 squared. So you see that allowance of a minus sign really could be crucial to get this type of a result. You may not be able to do this with p, but if you allow minus p instead, you get a very nice clean equivalence between a modular arithmetic condition and solving certain equations in the integers. And you may need that minus sign. Sometimes you may not. It just depends on the situation. Okay, so I want to talk about where this comes from. So I want to prove this theorem. Well, how do you go from a congruence condition, if d is a square mod p, to writing plus or minus p, one of them at least, in this form? So this is a kind of result when I was a student that I learned it. Actually, I first saw a proof when d was minus 1, studying Gaussian integers. Then I saw that the argument could be adapted to d equals 2. And then I saw the argument could be adapted to d equals 3. So, of course, since I did it that way, I think the best way to appreciate this theorem is to see special cases. But we have limited time here, so I'm just going to prove the general case. But it might seem like the argument I present, if you've never seen this kind of thing before, just comes out of nowhere. But in practice, I think these kinds of things were learned or discovered in particular examples before people caught on that there's an argument that could be used in general. This concept of unique factorization kind of saves the day. So let's show if d is a square, we're going to turn that into the right side, writing plus or minus p in this form. So d is a square. So that means I can write d as n squared. That's supposed to be the letter n. Mod p. And so that means p divides the difference. P divides n squared minus d. Now, if I look in the larger ring, when you have a divisibility occurring, the divisibility is also true in the larger ring, the same terms. But in this larger ring, I can break up n squared minus d. It's n plus root d, n minus root d. So if d was minus 1, we'd be writing n squared plus 1 as n plus I, n minus I. And just so you kind of have to appreciate 1 is minus minus 1. And so then what we can do is we have divisibility in the larger quadratic ring z bracket root d. And so now comes the key step. We have to appreciate that a prime number may or may not be prime in a larger ring. I'm going to use the term irreducible, since when we talk about things with unique factorization, in the integers we say prime composite. Maybe in a more abstract setting we talk about reducible and irreducible things. We don't say composite polynomial, I don't know. So, right, a prime number may or may not be prime, right? So, for example, like, again, let's go back to z bracket I. Right, 3 stays prime. There I go. 3 stays prime. Let's just say 3 is irreducible. but 2 is 1 plus I, 1 minus I, and 5 breaks up. 5 is 1 plus 2I, 1 minus 2I. So a prime in Z may or may not be prime in a larger ring, may or may not be irreducible in a larger ring. And so we're going to take cases. In fact, we're going to show that from this condition, the important condition here is this one here. We went from, right, we had P dividing n squared minus d. We interpreted it as P dividing n plus root d and minus root d. And so what we're going to do now is we're going to show that P is reducible and the way we're going to show that is by showing it's not irreducible. We're going to use that divisibility condition to help us do this. So the point is, if you're in a unique factorization domain, if P is irreducible, and Z bracket root D has unique factorization, then divisibility into a product implies divisibility into one of the terms. Who knows which? Well, of course, I guess if you know about conjugation on quadratic rings, if one of these happens, the other one has to happen. But in any case, irreducible goes into a product means it has to go into one of the factors, which means some multiple of P in this ring has to be one of those numbers. Oops. The problem is, when you look at both sides of this equation, there is an issue on the coefficient of root d. If you just look at the coefficient of root d, the integer coefficients match on both sides, so a multiple of p is 1 or minus 1, and that is certainly not true. So, in fact, because of that divisibility, it means P cannot be and Z root D having unique factorization. P cannot be irreducible. Thus, P is reducible. So now we get to a subtle point. What does it mean to be reducible? Anybody who's looked at unique factorization or just in algebra, terms reducible and irreducible in a domain when you're factoring things. What does reducible mean? You can factor it as a product of non-units. Very good, right? People might say you can factor it as a product of two terms. This is false. You have to resist the urge to say that. Everything is a product of two terms. X is x times 1. There is absolutely no content in saying that something is a product of two terms with no further qualifications. It's a product of two non-units. Okay, so in other words, P has to be a product for alpha and beta in Z root D that are not units, not invertible. Now, in fact, I've kind of glossed over a subtlety here. If something is not irreducible, that really doesn't make it reducible. Maybe it's instead a unit. But in Z root D, P times something cannot be 1. You can't have P times A plus B root D equal to 1. Right? Just look at the coefficients on both sides. So an integer other than plus or minus 1 would never be a unit in Z root D. So it's either irreducible or reducible. It's reducible here. So it's a product of things that are not units. Now, how do I make any progress on this equation? So here's a new equation. Let's highlight it in another color. Alpha and beta that are not not units. So how do we do anything with this equation? So now it's time to do the one thing you always do when you're not sure what to do. If anybody who knows me, what do you need to do at this point? If you're working on a quadratic ring, you have a multiplicative situation going on, take the norm, right? So it should not, based on how often you need to do that, the subject should be not number theory, but norm theory. Always norms show up in all kinds of settings all over the place here. So it's time to use norms. So now we're going to use norms. By which I mean the function, the norm function, n, from z root d down to z, the norm of a plus b root d is a squared minus db squared. Or I could call that alpha. This is alpha, alpha bar. By alpha bar, I mean the conjugate in the algebraic sense, a plus b root d, a minus b root d. So that's the conjugate. And so the crucial property of the norm here is that the norm is multiplicative. Norm of alpha beta is, so norm alpha, norm beta. This is simply a calculation. You sit down and you do it, and maybe at a later point in your studies, you learn that norms can be interpreted as determinants of certain matrices. So this multiplicativity of the norm is actually a kind of reflection of the multiplicativity of determinants, but you don't need to know that. You can just sit down and just do the math, and it works out. Another thing worth noting is that for integers, the norm is just the numbers squared, right? Because in that case, maybe I should write a here. Norm of a is a squared for an integer. So then let's go back to that equation. When P is a product of non-units, if you take the norm on both sides, and you win the battle against the stylus, norm of P is norm alpha beta, so P squared is norm alpha, norm beta. And the important point here is that once you take norms, you're now back in the integers. And so you have two numbers, norm alpha, norm beta, whose product is a square of a prime. So what are the possible values for the norm of alpha? P or P squared, or 1, or minus. Don't forget the minus signs. In fact, this brings up a key point that I had not mentioned here. Notice that when d is negative, then a squared minus db squared is positive. So on imaginary quadratic rings, the norm is always positive. But if d is positive, a squared minus db squared, it could be positive or it could be negative. So for instance, norm of 1 plus 2 root 2 is 1 squared minus 4 times 2 is negative 7. Norm of 3 plus root 2, 9 minus 2 is 7. So you need some experience working with this to be able to make these calculations in your head, but you can just sit down and just work out the formula. And so you have to, don't forget, norms could be negative unless d is itself a negative number, in which case norm is positive. Sounds very confusing. And so therefore, the norm here is plus or minus 1, plus or minus p, or plus or minus p squared. Now, in fact, the norm cannot be 1. If the norm were equal to 1, then alpha alpha bar is 1, which makes alpha a unit, which is not the case. And it can't be minus 1. If it were minus 1, you still get now alpha times minus alpha bar is 1. And so you still run into a problem. Because we were assuming that alpha, and we know being reducible, we have a product of p as two non-units. And so in the same way, just by changing alphas to betas, the norm of beta also is not plus or minus 1, because beta is not a unit. If neither number is plus or minus 1 and their product is p squared, the only option then for the norm of alpha has to be plus or minus p. And so then you just write you write alpha as p, plus or minus p is a norm, so you write alpha as x plus y root d, and so then you get one of these numbers, we don't know which, is a norm, and so then we get x squared minus dy squared, and that's exactly what we wanted. We wanted to have one of those plus or minus p as this expression, okay? And so, again, if you have not seen this kind of argument before, it kind of might seem like a blizzard of things being thrown at you, but I think it's very instructive to work through this, say, when d is minus 1 and d is 2, so you can look at the imaginary and real quadratic cases and see that it's the same argument, except that when the d is positive, you may have negative norms, so you have to worry about plus or minus signs. It's worth pointing out here. So if the d were negative, then minus p looking like this is not going to happen, because when d is negative, it makes the right side a sum of things. So we could say if z root d is a unique factorization domain and d is negative, then we get an equivalence without worrying about the minus sign option ever showing up, right? Like take d equals minus 1. Minus 1 is a square if and only if p is x squared plus y squared. You can never have minus p. But when d is positive, it could go both ways, okay? For positive d, sometimes if minus p looking like this, sometimes this actually implies p also looks like this for some other integers, x prime and y prime, but sometimes not. Right? So we saw an example of that. Minus 11 is 1 squared minus 3 times 2 squared, but 11 is not of that form. So there could be a crucial distinction to be made there. It's all about whether, well, in fact, let's address when can that happen? How do you tell that you might need the minus sign there? So the point is, if you wrote minus p, if this were to happen, then you can write p as the negative of the norm of x plus y root d. I'm just moving the minus sign to the other side. And so if minus 1 is itself a norm, in other words, if you can write minus 1 in this way, then you can write the minus sign as a norm, and you already have that other norm. Whoops, error. If minus 1 is of this form, then minus 1 is a norm. You already had that other norm, so I'm just rewriting that equation in this way. If d, but then the norm is multiplicative, so you can absorb the minus sign into the norm. And then you just write this product in its own way, right? Call that x prime plus y prime root d, and then you're done. You've written P itself. Okay, so for example, this seems too abstract. Earlier, we had seen that, where was it? Up. So minus 7 was 1 plus 2 root 2, taking d equal to 2. 1 plus 2 root 2, excuse me, minus 7 is not 1 plus 2 root 2. I know that's not true. Minus 7 is the 1 minus 2 times 2 squared, 1 minus 8. So this is a norm of 1 plus 2 root 2. So 7 is the negative of a norm. But the point is, minus 1 is itself a norm of 1 plus root 2. Right? A squared, this is right, norm for d equals 2 is x squared minus 2y squared. 1 minus 2 is minus 1. Minus 1 is a norm. And so if you write that as a norm, then you can bring them together on the inside. And now you have to, now you just multiply things out. And what do we get? 1 plus 2 times root 2 squared, so that's 4, is that 5? 1 plus 4 is 5, plus root 2 and 2 root 2, is that 3? 5 plus 3 root 2, 25. Minus 18, it worked. Okay, so from writing negative 7 as a norm, we got 7 itself as a norm. Notice earlier I had written in red 7 as the norm of 3 plus root 2, which is a simpler looking thing. So I got 7 as a norm here from minus 7 as a norm, but I didn't get the expression I saw earlier for 7 as a norm. So there are lots of ways of writing a number as a norm sometimes. In any case, the point is that, I should have written 5 squared minus 2 times 3 squared. 25 minus 18 is 7. So from writing negative 7 as an x squared minus 2y squared, because minus 1, this is the crucial thing, when minus 1 is a norm from z root d, you can absorb the minus sign into the norm, and so you can actually replace the plus or minus p with just p alone. All right, so that kind of explains situations where you can do that. And to appreciate this, if we can't do this trick for 3. That was the case when d was 3. Right? We saw that 11 was not a norm, but minus 11 is. And in this setting, the negative sign is not a norm from z root 3, simply because if you look at both sides of that equation, you cannot, by reducing mod 3, if that were true, minus 1 would be a squared mod 3, but minus 1 is 2 mod 3, and 2 is not a square mod 3, because the only square mod 3 is 1. Non-zero square is 1. So the failure of that example with d equals 3 is getting a minus 11, but not 11, is tied up with the fact that minus 1 is not a norm from z root 3. So it's kind of a tricky situation to decide when can you write minus 1 in this funky way. If you can, that's great, and if you can't, you have to allow the minus sign as a possible option in that theorem here. Again, the plus or minus is kind of a crucial thing here. Yeah, any questions? Yes? The question is there a constructive version of this where can you solve for x and y? So that's a good question. Certainly not going to say it's a bad question. Yeah, but it really is a good question, right? So there, yeah, so let's pose this as a question, right? So when plus or minus p has an integer solution, how can we find, or can we find, right, so, oh, yeah, right, let's see. How can we find the x and the y? In fact, we can just even consider this. You don't have to have plus or minus a prime, just even any number. If you know that a number, or just for any integer n, how can and d, an integer that's not a square, right? How can we decide if you can write n in this way and solve for x and y when they exist, which may implicitly include determining that they don't exist. So the first case that's important to understand is n equals 1. Okay, if n equals 1, x squared minus dy squared equals 1. If I say it has an integer solution, that's obvious, 1, 0. The point is it has a solution x, y in positive integers. Okay, so this goes under the name of Pell's equation. You just Google Pell's equation, and you can find a discussion of this. So you can solve for this in positive integers, no matter. I'm going to focus on when d is a positive integer. If d is a negative integer, x squared minus dy squared is a sum of, like, I'll say sum of squares, but imagine like x squared plus y squared, x squared plus 2y squared, x squared plus 3y squared. That's a sum of positive stuff. And so if you're trying to write a number as a sum of positive thing, that's a finite search, right? If I want to write is 101 is 10 squared plus 1, bad example. If I, whatever, 1001, well, if you wanted to write a positive number as a sum of two squares, in principle, the x squared and y squared are automatically in a bounded region, bounded by the number you're looking at. And so it's a finite search space, obviously, and therefore, just leave it to the computer to search. Okay, so the interesting case is trying to determine when you can write a number like this, when d is like 2. Can I write a number as x squared minus 2y squared, or x squared minus 3y squared? So let's consider this is known. And so when d is a positive integer, you can find solutions x and y to this kind of an equation, and it's not at all clear how to do that other than a brute force search, but you could, for example, continued fractions, you might use the continued fraction expansion for the square root of d and the convergence for that, lead to a systematic method of discovering, in fact, the kind of smallest or first solution to this kind of an equation. If you don't know what that means, you could rewrite this as x squared equals dy squared plus 1. And you just start hunting. Y equals 1, 2, 3, until you discover dy squared plus 1 is a square. And then you declare that to be x squared, and you found your solution. Now, that this will terminate, this will work because there is a solution, but this kind of brute force search could take a while because even if d is relatively small, the first x and y solutions could be quite large. So the continued fraction method is kind of a better overall technique, but if you don't know anything else, at least separating the variables, not in the PDE sense, but just moving the term to the other side sense, then you just, I've done this, you go to a computer, you just say, give me a vector, the first 100 terms, y 1 to 100, is dy squared plus 1 a square? And when it is, tell me that, and I see where that first occurs, then I discover a solution. So if you don't know continued fractions, you could always do that for n equals 1. So we should consider this as known, how to find a positive integer solution to this equation. So it turns out, fact, in terms of such a solution, in terms of some, by some I mean any, or in terms of some solution x naught y naught to the Pell equation, if you can find some solution in positive integers, I'll say there's a finite search space for the existence of a solution to x squared minus dy squared equals n for each n, even if n itself is negative for each non-zero integer. But by which I mean, it's possible to say, look, if you can find a solution to x squared minus dy squared is 1 in positive integers, you take those, the x and y that work there, and using that, and using n, and using d, I can give you a box, well, it's in 2 dimensions. I can give you a square, a rectangle, defined in terms of the Pell equation solution and d and n, so that if there's an integer solution to this equation that I just underlined, then there must be one within a certain bounded region of x and y. And then you go hunting through there, and if you don't find a solution, you're done. There's no solution at all. And if you found a solution, well, you found a solution. So, and in fact, yeah, so that's what I'll say on that. So you can make this an effective procedure in terms of solving Pell's equation. So it kind of all boils down to that. If you can do that, then the general case can be turned into a finite search space, which depends on n. Okay? So you can talk to me about that after class if you're interested in how that works out. But the whole study of x squared minus dy squared when d is positive is way more complicated, just because big x and y can have tiny x squared minus dy squared. I mean, think about the graph, x squared minus dy squared equals n. If d is a negative number, that's really the equation of an ellipse. And I think x squared plus 2y squared is n. It's an ellipse. But if d is positive, x squared minus 2y squared is n, it's a hyperbola. And so, an ellipse is going to have only finitely many integral solutions. Hyperbola, I mean, sure, it has lots of real solutions. It could have an integer solution way, way out, far away in large x and y. So there's a big difference in practice looking for solutions when d is positive or when d is negative. Okay, so any other questions? Yes?
If negative 1 is not a norm, is it decidedly impossible to always?
Right, so the question that was asked was, right, I showed you if minus 1 is a norm, that you can get rid of the minus sign, and is it the case then that completely explains when you can get rid of the minus sign? And so I was thinking about that last night. So I think when you're talking about primes, I think that is the complete determination. I think the answer is yes, but I did not have time just to check that over. So I will look at that later today and get back to you on that tomorrow. But I believe the answer is that if you, I guess the point is, right, if you can write p and minus p as norms, that should imply that minus 1 is itself a norm. You have to be careful, right? We're talking about things with integer entries, right? If you write, n is a norm, minus n is a norm, p is a norm, minus p is a norm, you can solve for minus 1 as a norm by taking a ratio, but then you have a norm with rational x and y. And it kind of comes down, if I can solve this equation in rational numbers, does it have an solution in integers? Maybe, maybe not. Things could be tricky. So I'll look at that and get back to you. Yeah. All right. Now, we had a running hypothesis here that everything was based on if z root d has unique factorization, then we get this nice equivalence, which is nice because the condition that d is a square mod p, thanks to quadratic reciprocity, you can turn that into a condition on p mod for d. Okay? So that's the condition of checking whether a prime has d being a square mod that prime can be turned into a Conrad's condition on p. So we feel like we understand that thanks to quadratic reciprocity. But we had this big assumption. If z root d is a u of d, then you have this equivalence. But what if it isn't? Okay, what if z root d is not a u of d? So then this whole method of getting the equivalence, getting that converse non-obvious direction kind of breaks down. Sorry, so what if z root d does not have unique factorization? So let me show you, let me point, I will just point out an example, okay, that if you take d equal minus 5, so in this case, z root minus 5 does not have unique factorization. Does anybody know an example of, wait, hold on a second. I forgot to point something out here. You see, remember we had that example. So as a corollary of the theorem, right, the theorem said if z root d has unique factorization, then we get this equivalence. And so the point is that if d, how did I want to put that? I think I had that as, thought I had that written down in my notes as a comment here. So if d is a square mod p, and plus or minus p, and now I really mean both of them, not one of them, but both of them, is not an x squared minus dy squared, then we've just shown that, we'll someday get this to work. Why is it there's a constant struggle against that? Then z root d does not have unique factorization. Right? If it had unique factorization, we get an equivalence between d being a square mod p for all primes. So this is for some prime p. If d is a square mod p and neither p nor minus p looks like that, then z root d does not have unique factorization. So for example, we've already seen an instance of this. 10 is a square mod 3. 10 is 1 mod 3. But neither 3 nor minus 3 looks like x squared minus 10y squared. Why is that? How do we know 3 is not x squared minus 10y squared? Anybody see why 3 and minus 3 cannot be written as x squared minus 10y squared? Yeah. Reduce mod 5. Neither one. And so this fact proves that z root 10 does not have unique factorization. It's always intriguing when you can show if property fails without checking the property. Like, I have not given you a counterexample to unique factorization in z root 10. I've instead shown you z root 10 does not satisfy a property that all z root d's with unique factorization satisfy. And so it's kind of, wow. So it does not have unique factorization. That's kind of a curious way to show something doesn't have unique factorization. Now, what if z root d does not have unique factorization, by which I mean if, so. If z root d does not have unique factorization, is there such a p? So I'll just show you an example. Z root minus 5 does not have unique factorization, so what's the famous example? Direct 6, right? So this goes back to, I think, to Dedekind. 6 is 6 is 2 times 3. Why is this not? 6 is 2 times 3 is 1 plus root minus 5, 1 minus root minus 5. And these are all irreducible, right? You don't, simply writing a number as a product in two ways doesn't prove anything, right? 100 is 10 times 10 is 4 times 25. That doesn't mean we have a counterexample to unique factorization in the integers. You have to check that the factors are actually irreducible and not unit multiples of each other. And so in this case, I will leave it to you to check for primes P that are congruent to 3 or 7 mod 20, like 3 and 7 themselves, or 23, and so on, you can check that D, in this case, minus 5, is a square mod P, but plus or minus P, really only use the plus sign because D is a negative number here, is never x squared plus 5y squared. So there are tons of primes that exhibit the failure of that converse direction. And so in a broad sense, there are many z root Ds where you could say, like D is square free and not 1 mod 4, that when these things don't have unique factorization, there will always be such primes. So this peculiar method of showing that a z root D doesn't have unique factorization, actually quite often it really will work. There's kind of a predetermined guarantee on that, okay? Anyways, I've seen I've gone a little bit over time, so I think I'll stop here. Thanks.